Hello. Now we will calculate the moment of inertia for a ring element. So I'm having a ring, and for this ring, the mass m is given and the radius is r for this ring. And we want to calculate the moment of inertia for this ring about the axis which is perpendicular to the plane of the ring and passing through the center of mass of the ring. So this is my axis. So the axis is like this. So the motion of the ring will be happening either clockwise or anti-clockwise, okay, about the axis. So for this kind of structure, we want to calculate the moment of inertia. Now, we have to cut the element, obviously. To cut the element, we have to move perpendicular to the ring. So if I move perpendicular to the ring, meaning if I move in the Cartesian coordinate system, there is a problem, actually. If I move in a Cartesian coordinate system, meaning in terms of x and y, the elements onto the ring will be having a little bit difficult relationship. So for these kind of structures which are circular in nature, we generally tends to go by the variables, circular variables, okay, and those circular variables are theta basically. We don't take the variable here in terms of x and y, we take the variable in terms of theta, angular variable we cut. So we'll learn how to cut that. So in this case, what we will do will not go for x. What we will do with respect to x-axis, we'll draw a line. With respect to x-axis, at an angle theta, we will draw a line, okay. So we are moving in a plane basically, and we are changing this line. So first we go for theta, and then further d theta we will be going. So next time we will make a line which is having an angle theta plus d theta with respect to the x-axis. So this is the second line, okay. So I made two lines. One line which is making an angle theta with the x-axis. Second line which is making an angle theta plus d theta with respect to x-axis. Between these two lines, I am having this element. This portion of the ring is being between these two lines, and let's assume the mass of this element is dm. So this will be our test element. We will be calculating the moment of inertia for this element, and from there we will try to integrate it. We will try to calculate moment of inertia for the whole object, okay. Now I have to calculate the mass of this element. So before that, I have to calculate the length also. This is the length. So you see, this element is circular in nature, and this angle here is d theta, and the radius is r. So if this length is ds, in that case the ds will be equals to r d theta from circular kinematics actually. So the length of the element is r d theta. Okay, we have calculated that. We can write it separately. So ds is r d theta. This is the length of the element. Now we want to calculate the mass. But before calculating the mass, I need the length. Along with that, I need the density also. So ring, though it is a two-dimensional element, here it is a two-dimensional element, but the mass is concentrated onto a line, which is a circular line. So here in this case, I'll define the density, linear density. I'll not define the areal density, I'll define the linear density. So linear density, which is lambda, will be defined as the total mass, which is m, I've defined, divided by total length. So total length of the ring is 2 pi r, which is the periphery. So that is 2 pi r. I'm assuming one thing here, I'm assuming the linear density to be constant. So this is constant. So that's my assumption right now. So if the linear density is given in terms of theta or in terms of some other variable, we have to take that linear density. So if examiner is not saying anything about the linear density, we have to take it as a constant. Okay, so linear density we get. So now we have a relationship for the mass. Mass is linear density multiplied with the length of the element, which is ds. We'll put the values. So dm becomes r d theta, which is the ds, multiplied with lambda, which is m upon 2 pi r. So this r and r will cancel out. So mass of the element will become m upon 2 pi times of d theta. So now we got the mass of the element also. So we got the mass of the element. Now we have to calculate the moment of inertia for this element. Okay. So if you see, this element is a point element, and we know the moment of inertia for the point element. So moment of inertia for point elements is defined by mr square. This is the formula. This is the formula for moment of inertia for point elements. So I can use this formula. In this formula, m is the mass of the point and r is the distance of the point with respect to axis. So distance of the point element in this case with respect to axis is capital R. And the mass of this element is dm, which we have already calculated. So the moment of inertia for our element DIO, I am defining it, O is the axis, will be dm into capital R square. From the formula mr square, in place of m I am writing dm because that is the mass of the element, and in place of small r I am writing capital R because that's the distance of the element with respect to the axis. So let's put the values. So it is r square multiplied with m upon 2 pi times of d theta, or DIO will be equals to mr square upon 2 pi d theta. So that becomes the moment of inertia for the element about the axis O. Now since we want to calculate the total moment of inertia of the body, so the body we can create by adding all these elements. So since we can create the body by adding all these elements, similarly I can add the moment of inertia also, because this moment of inertia and the moment of inertia I want to calculate, both of them are having the common axis. So that will be DIO. So let's put the values. So mr square upon 2 pi, we will be taking this thing out of the sign of integration because variable is theta and mass and radius does not depend upon the angle d theta. So this sign you see, this is a sign for complete integration. So we have to take the limits for this. We have to take the limits in such a manner so that the whole object should be covered. So we have to take the limits for theta. So obviously if I start theta from 0 and if I move the theta till 2 pi, my whole object will be covered. So I'll be going from 0 to 2 pi. If I do the integration, I'll be getting this integration of d theta is theta from 0 to 2 pi. Let's put the values. So I will be equals to mr square upon 2 pi minus 0. First we put the value of theta by upper limit, then minus we replace the theta by lower limit. So this whole value will become 2 pi and 2 pi will cancel out. It will become mr square. So this becomes the moment of inertia for the ring, but not for all the axes. This is the moment of inertia for the ring about the axis which is perpendicular to the plane of the ring and passing through center of mass. So like when there is a wheel, so wheel performs the motion about its center of mass. So when we will calculate the moment of inertia for the ring about the axis which is passing through its center of mass, this will be the moment of inertia. We have to take it there. Okay. And while deriving this formula, if you remember, while deriving this formula, this is the assumption we have taken. That linear density we have assumed to be constant, meaning we have assumed the total mass, the mass distributed onto this ring is uniform everywhere. So if the mass is not uniform, we have to restart solving it from this point itself. But the process, the whole process will remain same. You will be getting the different result for the same axis corresponding to the variable lambda there. Okay. So that's how we calculate the moment of inertia for the ring. And this formula, you should be memorizing this formula. Okay. Thank you.